Hello everyone and welcome back to part 3 of chapter 22. In the previous video we derived the electric field magnitude of a ring of charge, and for this ring of charge the charge was uniformly distributed about the ring, and the point at which we're going to measure the electric field magnitude was some distance z above the center of the ring, and we needed it to be directly above the center of the ring so that we could take full advantage of the symmetry in this system. And then after we had the expression derived, we went through and we actually rewrote our solution so that it would better fit to a laboratory situation, because in our original solution we had values of little r and theta, which are not the easiest thing to measure in a lab setting, especially if you're going to be varying values of big R and Z with different experiments. But if we can measure big R and Z, which are actually going to be easier to measure than little r and theta, then if we do need to make any changes to the system, it's actually quite easy to calculate the new value of little r and theta from the values of z and big R. And so that's why we have the ring expression as we see it here on the screen. And then we played what I called the what if game, which was where we took our expression to the different extremes, letting z equal 0, letting z equal infinity, and the same thing with r. And when we did that, we found that if we let z equal 0, then the electric field will go to 0. And if we let z equal infinity, the electric field would go to 0. And that meant that somewhere in between 0 and infinity, our electric field would have to have some maximum. And I closed out the last video asking you to think back to your time in Calc 1, where you have a given function and you're trying to find out where that function will achieve its maximum value. Now we can try just randomly plugging in values for z until we achieve something that looks like it's a maximum, but that's just guesswork. There are ways of using the calculus and the math to actually show that we are achieving a maximum for our function. And that actually comes from looking at the slope. As our function changes, our slope function changes with it. And when we get to that maximum electric field magnitude, what we see is that the slope of the function at that point is 0. So if we can figure out a way of describing the slope of the function, we can then set that to 0 and solve for the appropriate value of z that causes that to happen. And in finding the slope of any function, what we have to do is we have to take a derivative. And in this case, we're going to be taking the derivative of our newly derived electric field function with respect to z, and then we will set that equal to 0 and solve for z. So I'm going to bring the the electric field function down here. It's our field function. And we need to take the derivative of this with respect to z. Now, z is going to be our variable. Everything else in here we'll assume is going to remain as a constant. So we can bring the k and the q value out front for right now, and we'll incorporate those later. But for right now, the only thing that really needs to be inside of the derivative are these terms, which include our variable z. And z is present in both the numerator and the denominator. And when this happens, back in calculus, we learned ways of taking derivatives. We had things like the product rule, the quotient rule, the chain rule. So all of those are applied at the appropriate case scenarios. But what we have here is a fraction of z over the quantity z squared r squared to the 3/2 power. And it is possible to rewrite the quotient rule and apply it as a product rule, but that would involve changing the signs of the powers, and that's not something that I want to mess with right now, because ultimately our job is that we're going to have to set this equal to 0, and I don't want to be messing around with any negative powers in that case. So we're going to suffer our way through that quotient rule. And if you remember your Calc 1 and your quotient rule, there was a little mnemonic that went with it. I believe it was low d high minus high d low all over low squared. So low referring to the terms in the denominator, high referring to the numerator, and then the tick marks there are indicative of a derivative. So we need to take the denominator, and I'll put all of this in a bracket here. I need the denominator, which is low, z squared r squared 3/2 power, times the derivative of the numerator, which is just 1, minus the numerator, z, times the derivative of the denominator. Now the denominator, z squared r squared to the 3/2 power, we will have to use the chain rule to find the derivative of this, because everything is currently encased by that parenthesis set and taken to a power. And so our chain rule basically says start from the outside, work your way in. So we're going to bring down the power. We have 3/2 z squared r squared, and then we have to reduce the power by one integer, and so 3/2 minus 1 is going to be 1/2, and then we have to take the derivative of the terms inside our parenthesis set, which is z squared r squared. And so we're taking the derivative with respect to z. We're going to get 2z, and that should be it. So that is the derivative of our denominator, and all that will have to go right in here with our other terms. So we have There's 3 halves and 2 z, so that's just going to come out to be a 3z, but then I'll pair it together with the z that I have out front here, which means I have 3z squared, and then everything inside of that parenthesis set, which is 1/2 power. So I'll just double check my algebra there. So everything looks good. And then all of this has to be divided by low squared. So I have to take the denominator and I have to square it. Now if I do that, oops, get rid of all this. If I take my denominator and I square it, well, now I'm taking a power to a power, and whenever we take a power to a power, we can multiply the powers together. So 3 halves times 2 is just going to be 3. So that means we have z squared r squared to the 3rd power. And that's it. There is the derivative of our electric field function, and we have to set that equal to 0 and solve for z. And I can just about hear some of you choking right now, thinking, where are we going to start with trying to solve for z? And I agree, this looks like a very daunting task, but we're going to take this one step at a time, and I can assure you that the math is going to clean itself up very, very nicely. The great part about this is that in solving for z, keep in mind that everything has to collapse down to equal 0. So first of all, take note that over here we're multiplying by kq. Both of those are constants. And so if I divide each side by kq, well, I still get 0 on the right. So the k and the q are not going to actually contribute to causing this expression to go to 0. As for the rest of it, there are 2 ways that this expression can collapse down to 0. One way is if the numerator goes to 0, or if the denominator goes to 0. Excuse me, not 0, infinity. These are the two ways that the entire expression could go to 0. Now, the denominator, z squared r squared to the 3rd power, we talked about a couple of different case scenarios where, you know, we could let z go to infinity, we could let r go to infinity. In those cases, yeah, if we allowed z and r to go to infinity, then we would achieve one of those extreme case scenarios. But keep in mind that we want to remain somewhere between 0 and infinity. So we're not going to allow either of these values to go to any of those extremes. We want both z and r to remain finite, measurable quantities. And if that's the case, if neither of these can go to 0, then the entire denominator cannot cause our expression to go to 0. So if we forbid this from going to infinity, then the denominator cannot force our function to go to 0. But we can actually ensure that that doesn't happen by taking both sides of our expression and multiplying by the denominator. So if I take z squared r squared to the third power, multiply that to each side, r squared to third power, that will eliminate the denominator from the left-hand side, and 0 times something is still 0. And so now what we have z squared r squared to the 3/2 power times 1. I'm just going to drop the 1 there. Minus 3z squared, z squared plus r squared to the 1/2 power equals 0, because anything times 0 is still 0. So now we can see that it's actually the numerator which is going to be going to 0. This is the only thing that can cause our expression to go to 0. And now we can see that the math is getting much more manageable. The next step in solving for z is I'm going to take the second term in our expression, and I will add it over to the other side. So when I do that, when I add it over to the other side, basically we're just going to flip the sign on that term. So we get something that looks like this. And the next thing that we will do is, we can see here that we have some like terms on either side. We have some terms with similar bases. And, oops, I forgot my square on the r there. Now we have like terms on both sides. And so I'm going to divide each side of the expression by the z squared r squared to the 1/2 power. And that will get rid of those terms over there. We're left with 3z squared. And on the left, we have two like bases. We're dividing them. And so when we divide like bases, we can subtract the powers and combine them into a single term. And so 3/2 minus 1/2 would be 2/2, or 1. Z squared r squared to the first power, but we really don't need that parenthesis set anymore since it's just to the first power. And oh, this is looking really nice now. We can solve this no problem. We'll subtract a z squared from each side. So r squared equals 2z squared. We'll divide each side by 2. And then take a root for each. And so z, the value of z, which will cause the derivative to equal 0, occurs at r over root 2. And keep in mind that anytime we have a square root, we have a plus minus as a consequence, and so our answer will be plus or minus r over root 2. Now, should we just drop that minus sign since we're looking for the magnitude of z? Does that minus sign even have a meaning for us? And it actually does. Since we have this ring with a bunch of charges on it, we're asking ourselves, where does this electric field function have a maximum value with respect to z? So where are we going to find our maximum value? Well, we can either go positive r over root 2 above the ring and achieve a maximum electric field magnitude, or if we just flip our screen over, there's nothing that says that we can't drop below the ring. And so if we just go in the opposite direction, our electric charges are going to be sending electric field lines in all directions. It just so happened that we were kind of focused on what was happening above the ring. We didn't really consider field lines that were being projected down. But at that same magnitude of displacement, we would see another point in space where we have a maximum field magnitude. And so, now, whenever we come up with an expression to describe an electric field magnitude, and we want to know if there is a maximum value that can be achieved out in space somewhere, we now know how to do that. We're going to take our function, we'll hit it with a derivative, and then we need to set that derivative equal to 0 and solve for the variable term. In this case it was z. Now for a line function, if we think back to the electric field that was produced by the line, this function was dependent on 1 over z, I believe. And so if we were to take a derivative of that function, we would not actually find ourselves with a maximum. And that's because the further away that we get from this line, the more the function diminishes until we eventually equal 0. In other words, we would almost have to be sitting right on top of the line of charge in order to achieve a maximum. And unfortunately, the calculus only allows us to find a maximum if we actually have values that are lower on either side. The same thing can be said for finding the minimum of a function as well, because technically your derivative will equal 0 there. And if you have a function that oscillates, now you have multiple slopes of 0. So how are you supposed to know if you're dealing with a max or a min? And in that case, you had your second derivative test, which would indicate if you had a concave up or a concave down, and so you could tell if your function was actually at a maximum or a minimum at that case. But for the ring, we really don't have to worry about that because we only have the one case scenario of a maximum. We start at 0. and we eventually go back to 0. And the math kind of supports that, because when we solve, we only got one location in the given direction where we actually achieve a maximum. The other position there is if we travel in the other direction, but traveling up, we're only going to encounter one maximum for this particular case scenario. All right. So that is the ring. Now we want to consider what would happen if we took that ring of charge, and instead of having an infinitesimal ring, what if we gave the ring some thickness? So what if that ring had some surface area to it? And we'll just go ahead and take that ring and we'll fill it in completely. In other words, we have a disk. So our disk has a maximum radius of big R, and we're going to uniformly distribute some charge over the surface of this disk. So I'm going to draw a whole bunch of little positive signs here. So remember, with any conducting material, the charge will uniformly spread itself out about the surface. So we once again have the necessary uniform charge distribution. But this charge is now distributed about a surface area. The previous two discussions, we had our charge distributed over a length. Now our charge is distributed over a surface area. And so we are going to call this our surface charge density. We have charge per unit surface area, and we will signify this using a sigma. So sigma is our surface charge density, and this is very similar to what we had with lambda. Oops. Where lambda was the charge per unit length, or linear charge density. And lambda could describe either the full charge per unit length or the infinitesimal ratio of the two. Likewise, sigma can be used to describe either the full charge per area distribution or some infinitesimal sample. So if I were to come in here and just take a sample of this disk, the ratio of charge to the area that I sampled has to equal the same ratio as the total charge that was spread out over that disk. And so this is going to allow us to describe how the charge was distributed throughout the system. And that was very important with the previous derivations, because otherwise the only thing that we could do was add up the charge. And adding up the charge doesn't do us much good if we don't know how that charge was spread out in the system. All right, next we will choose a point where we want to measure the electric field that is being produced by this disk. And just like the ring, I'm going to choose a point that is directly above the center of the disk. mainly because I, once again, want to take full advantage of the symmetry in this system, but also because it's going to make the math easier on us as well. So we have a point P that is directly above the center of our charged disk. We'll go ahead and call that distance Z, same as we've been doing before. And you might be thinking at this point, well, we've already done the ring of charge. How much different can a disk be? Because a disk is really just a bunch of concentric rings all put together. And so if I had a whole bunch of rings and they're all producing electric fields up at this point P, what if I just added all those rings together? Then what would happen? Well, that's a pretty good idea. It's a pretty good starting point, and I think that holds some merit. So let's get ourselves a sample ring. And it's not a very good ring. I'll try that again. It's a little bit better. So I want to take a sample of that disk, and well, the big difference between this and the ring derivation that we did is that this ring actually has a bit of thickness to it. Previously, we did not assign any dimension to the thickness of the ring, and that's because we were assuming the ring to be infinitesimally thin. In this case, we can't do that because we're going to have to add up the thicknesses of all of the rings to achieve the finite radius of the disk. And so this ring segment right here, it has to have some amount of area, even though we're going to consider it to be infinitesimal. It cannot equal 0, so it has to be bigger than 0. On that ring segment, so this ring segment, which has a infinitesimal amount of area, it is host to a certain amount of charge, which we are going to call dq. And now we can see why we wanted our sigma value there, because for this ring of infinitesimal thickness, there has to be a certain amount of charge present on the surface of that ring. For every other ring that we try to put in here, so maybe there's another ring which is smaller, and let's see what color I should use. Maybe I'll try this. I'll try purple. So this next ring here, that ring is also going to have an infinitesimal surface area, but obviously it's smaller than the first one that we drew. But that's okay, because regardless of what ring we're trying to sample, every ring has to have the same ratio of charge per unit area. So every concentric ring that we use will have a different amount of charge and a different area, but the ratio of all of those rings has to be the same. So therein lies the beauty of our uniform charge distribution. All right. Next, we need to go back to our default expression for electric field magnitude. So we're going to start with our individual charge expression. And since we're once again using infinitesimal amounts of charge, each infinitesimal charge will produce an infinitesimal amount of field. And let's see here. Well, each ring segment that I use will have that infinitesimal charge. I just need to know now how far is each one of those ring segments from the point P where I'm trying to measure things. And it's at this point that I need to make a slight adjustment to our notation. I don't want to use little r to measure this distance, even though we've been using little r in all of the other derivations. I actually want to save little r to measure the changing radius of the rings that we're making. So this infinitesimal ring of charge that we're going to be using, it has an inner radius value right here, which we could call little r. And then there's that thickness that we talked about. And so that means that there is an outer radius for this ring. And, well, how thick are we going to allow this ring segment to be? Considering that we've already assigned infinitesimal charge and infinitesimal area, we might as well say that this ring has an infinitesimal radius to it. And so that means that the outer radius of the ring would be r plus dr. Well, since we're using little r to describe the changing radius of the disk, I need something else to measure the distance between our charges and where we're trying to measure our field. And so, well, I'll just use d for distance. And that means I need to replace little r with d. All right. Next, we start to set up our integrals, and again, looks like we're going to be integrating with respect to charge, but if I just integrate with respect to charge, all I do is add up the charge. I need something in the expression that describes how the charge is distributed through the system, and that is right here. That's our sigma value. So the infinitesimal charge will be based off of the surface charge density sigma times the infinitesimal surface area. So we have K, we have sigma, we have dA, and d squared. And so now it looks like we're going to have to integrate with respect to the surface area, which should make sense because eventually we're going to have to add up the contribution of all the charges that are on the surface of this disk, except what is the surface of this disk dependent on? Well, it's dependent on the radius. We have changing radial values for each concentric ring that we're going to add up. Eventually, we're going to have to add up all the rings from 0 out to big R. But that means that if we're going to integrate with respect to r, we're going to have to figure out how dA relates to little r. So for each concentric ring, I'm going to draw a ring of thickness dr. We'll zoom in a little bit here. So any given ring within this disk example will have an inner radius. So inner radius of r and an outer radius of r plus dr. And we need to figure out how does the area of this ring segment relate to the inner and outer radius values. Well, if I were to find the surface area that is described by the full outer circle, which is r plus dr, and then subtract the area that is defined by the inner radius, which is just r, then the difference of those two would be the area of the ring segment. And that's what we'll do. Each of these is just a circle, and so the area of the outer radius is going to be produced by, and our area expression for a circle is pi r squared, so we have pi r plus dr squared for the outer area. For the inner area, we have pi, and that's just r squared. And so the area of the ring segment, which we've been calling dA, is going to be the difference in these two terms. So we have the outer minus the inner, and that's how we're going to describe our infinitesimal area for each one of these rings. Now there is a bit of cleanup that we can do here, and you'll notice right here we have a binomial that is being squared, so we need to do the algebra correct. We need to FOIL that binomial, and when we do that, we get r squared plus 2 rdr plus dr squared minus the second term pi r squared. And here we actually have some stuff that will cancel out. The pi r squared back here will cancel with the pi r squared up front. And that leaves us with pi 2rdr plus dr squared. And that is now the more simplified version of our area expression, which will have to be brought into our integral. The problem with this is that we have one integral that we can take, but we have a second order differential term down here, and that's not going to work. I can't take one integral and then still have a differential term left over. So here's what we're going to do. In our description of the thickness of each one of these rings. We said that each ring had a thickness of dr, and this thickness was infinitesimal. So essentially this thickness is almost equal to 0, but not quite. It's just a little bit bigger than 0. Well, what happens when you take a value that is almost equal to 0 and you square it? Well, we already know from experience, if we take a really small decimal value and we square it, it gets even smaller. So if dr is approximately equal to 0, then dr squared may as well be 0. And we're going to go ahead and make that assumption. So if dr squared is 0, then we no longer have to worry about that second order differential term. And we can now say that our integral, go back up here and remind myself what that was, k sigma dA over d squared is now going to equal k sigma, and we're going to bring in dA, which is now, let's see, we've got 2 pi r dr all over d squared, and that will have to be integrated with respect to little r, which is just fine, because little r is going to go from 0 to big R. So 0 to big R. The left-hand side, that will integrate to e. That's no problem. Let's take a moment and pull all of the constants from our expression out to the front. So that includes the 2 pi, the k, and the sigma. Everything else needs to stay inside. We have r dr and we have d squared. Now, why does d have to stay inside of the integral? Well, if we go back to our picture, d is part of the right triangle that has been formed with r and z, and well, who knows, we may end up having to deal with theta again. And because we're going to be integrating from 0 out to big R, as little r changes, theta will change and d will change. So I need to figure out how I'm going to represent d squared in terms of r and preferably z, because z is a constant. Well, I can do that, no problem. That's another Pythagorean theorem. D squared is going to equal z squared plus little r squared. So 2 pi k sigma r dr z squared r squared. And we can also put in the limits, because we said that r was going to have to be evaluated from 0 to big R. And we're just about ready to jump in and evaluate the integral here, except if you remember with the ring, because of the symmetry of the ring system, we have that evil twin effect going on, where a charge right here will send an electric field up to that point, and it will have an evil twin over here on the other side, sending an electric field line up. And those field lines are going to have components that will combine, because these components are vectors. We will have horizontal and vertical components, and just like the last two cases, these horizontal components will have to cancel out. And that means that we have to incorporate some kind of trigonometric function that ensures that only the vertical components of our field lines will survive. And so that quick fix was cosine theta. You can go back and review the previous two derivations. We saw why cosine theta was needed. So we're going to incorporate cosine theta into our integral, but, well, theta is a variable. As little r changes, theta changes. And that means I need to replace cosine theta with something in terms of r and z. Well, in that case, let's see, these three do not actually define cosine theta. Cosine theta is adjacent over hypotenuse. And I don't want d, I want r. But that's okay, because I know what d is. It's just going to be root z squared r squared. So that means that cosine is going to equal z over root z squared r squared. And that will go into our integral expression. And like before, in the denominator I have the z squared r squared of the first quotient there, which is to the first power, and we can rewrite the second one, we can rewrite the root as a fractional power. And so now we have 2 pi k sigma 0 r dr with a z, which is actually a constant. So I'm going to pull that out to the front. So it doesn't really need to be in there anymore. And then everything in the denominator can be combined into a single term of z squared r squared to the 3/2 power. Okay. So we're finally ready to take this integral. All this time has been spent setting up the integration process. Again, as I mentioned in previous videos, you are not expected to reproduce these derivations, but once we get to about this point right here, you are expected to be able to tweak some of these final integrals and be able to use the end result of these expressions. And so now what we have to do is we have to go through our integration. And looking at this, when it comes to taking integrals like this, it's it's not always that straightforward as to what method we want to use for the integration. The first thing that we're typically taught in calculus in terms of integration is a U substitution. And so we could try that. We could go through the different terms that we have in our integral there and try some kind of U to U substitution. And it looks like the best choice for U would be the term that we have in the denominator, which is z squared r squared. And so du would then be 2r dr. And will that fit into what we have? And it looks like it will work. We have the necessary r value in the numerator. We just need an extra 2, which, well, we can steal that 2 from the 2 that we had sitting out in front. And now what we have is the integral of du over u to the 3/2 power. And we can bring that power up to the top. All we have to do is change the sign. And then we take the integral of u to the negative 3/2 power. When we integrate, we add 1 to the power. So 1 plus a negative 3/2 would be negative 1/2. We then have to divide by the new power. And so what we have here is a negative 2 over root u. And so negative 2 over root u, we now go back up and we reclaim the value of u, which is z squared r squared. And so this is what is going to go in for our integral. Now we did steal the 2 from the front there, but the 2 is actually going to come back. It just sort of rode along in the integration process here, but we now have a negative 2. We have pi k sigma z all over root z squared r squared, which we now have to evaluate at our limits. And when we do that, we get negative 2 pi k sigma z. So all the stuff on the top there is a constant. I'm just going to factor that out. We have 1 over root z squared big R squared minus 1 over root z squared plus 0 squared. Now I'm not a fan of having this minus sign out front. So what I'm going to do is I'm going to take that and I will distribute it through the brackets. And all that's going to do is it's going to flip the order of the terms that I have in the brackets. And so we now have 1 over, I have root z squared, which is just going to be 1 over z, minus 1 over root z squared big R squared. Well, we're done, kind of. The one thing that we should probably bring to everyone's attention right now is that I have a z out front, which if I were to carry that through into the brackets would allow for a bit of simplification, because if I bring that z in to the top terms, I would have z over z, which is 1, minus z over root z squared r squared. And now we can play the what if game, in addition to bringing back sigma. You'll remember at the very beginning, sigma was there to help us describe how the charge was distributed over the area of each individual ring segment. Well, we're done with the integration now. We've added everything up, and so we can replace sigma with the full ratio of the full charge spread out over the full area of the disk. And so the full area of the disk is pi big R squared. So we have 2 pi k q over pi r squared, and that means that the pi's will drop out of the expression. And then we have everything left inside the brackets, exactly the way they were before. Alright, so now that we have that, we can play the what if game. So what if we let z go to 0? What happens to the electric field? Well, if I let z go to 0, what's going to happen here? If I let z go to 0, the term inside of the brackets, see, if I let z go to 0, then I just get r squared in the denominator, which is okay. I get 0 up in the numerator, but I still have some leftover materials. I still have the 2kq over r squared. And so the electric field at the center of this disk doesn't actually collapse down to a 0 like we would have expected for a ring. Kind of an interesting development there. What would happen if we let z go to infinity? So if we go to infinity, the second term within our brackets, I would have infinity in the numerator. I would have, let's see, z squared plus r squared. If the z is infinitely large, then r squared doesn't matter anymore. And so I would have infinity down in the denominator as well, which technically would be undefined, but let's try a different approach with this. If z is infinitely large, then r doesn't matter, and we get square root of z squared in the denominator, which is just z, which is 1. And so now inside the brackets I have 1 minus 1, which is 0, which is not defined. Now you may be asking yourself, how can we justify that as being 0 and not being the undefined value? Well, if we get infinitely far away from this disk, are we going to notice the disk anymore? And the answer is no. If it's infinitely far away, we're not going to see it. We're not going to register any influence from that disk, and so we should not experience any electric field from that disk if we're infinitely far away. So what if we let R go to 0? What would happen then? Well, in that case, if we let R go to 0, inside of the brackets, we would get 1 minus 1 again, which is 0. But then we would have a 0 squared down in the denominator. And so we kind of run into a similar situation as to what we had up here, where instead of infinity over infinity, now we have 0 over 0, which is also undefined. It is worth mentioning, even though you have an undefined value, that does not mean that a true physical value doesn't exist. It just means that the math is collapsing before it can give us an answer. So here's the logical line of reasoning. If we took this disk and we shrunk it down to a point of 0 radius, what would you get? Well, two ways of arguing that would be that you would either get a point charge of Q, in which case your disk would revert back to a point charge expression, or in the case of the disk, if you shrunk your disk down to a surface area of 0, how much charge could you fit on it? And if you have a disk of surface area 0, then you don't have room for any charge on it, which means no charge, no field. So I'm going to say that the electric field in that case is 0. Lastly, what would happen if you took your radius and you extended that out to infinity? So you're going to take your disk and you're going to stretch it out in all directions. Well, here's the big difference between the disk and the ring. If you stretched the ring out, well, you would be taking all the charge that was sitting on that ring, and you would be moving it infinitely far away from you, and you would no longer be able to see that ring. With the disk, however, you're not moving all of the charge away from you. You still have the surface area of that disk, and so you still have charge that is close by. The major difference here is that you now have an infinite amount of charge spread out over an infinite surface area, which again is technically undefined, but the ratio of charge to unit area has already been established. If we were to look at this infinite disk of charge and we took a sample of it, well, there would have to be a finite amount of charge per finite area, even though it's an infinitely large sheet. So this ratio is not undefined. We already know what it is. It's sigma. And what that means is that we would have to backtrack in our mathematics to the version of the equation that still involves sigma. So if our radius went to infinity, we would have to incorporate the value of sigma and use that. And what happens to the math? So what happens inside those brackets if we let r go to infinity? Well, if r goes to infinity, r squared plus z squared effectively just becomes root of r squared, or r. And so we're taking some finite value of z and we're dividing it by infinity, which we're going to let be 0. And so what do we have now? Well, we have 2 pi k and sigma. So the electric field is 2 pi k sigma for an infinitely large disk. Well, if the disk is infinitely large, how do you know it's still a disk? If we allow this disk to stretch out to infinity in all directions, how do you know it's still a disk? Well, we don't. All we can say now for sure is that we have an infinitely large sheet of charge. And somewhere above that sheet, a distance of z, the electric field magnitude is going to equal that which we've just found out there. Now, it's at this point in the book where our author is going to make a pretty big shift in the notation. We're going to take our k value, which we've been using 8.99 10 to the 9 for the value of k, and we're going to start replacing k with this expression, 1 over 4 pi epsilon naught. And if you're going along with the reading and some of the homework, you may have even already seen this pop up at some point. And you might be thinking, well, why do we have to do that? And what's this epsilon naught here? Well, we can actually solve for that right now because we know what the value of k is. Epsilon naught, with just a slight bit of rearranging, is going to be 4 pi k, or 1 over 4 pi k, excuse me. So 1 over 4 pi, 8.99, 10 to the 9. This is going to come out to be say 8 point. Can't get my eraser function to turn off here. Just a moment. So our value for epsilon naught trying to look this up here. Epsilon naught is the permittivity of vacuum, and so this is a This is a universal constant that describes how our electric phenomenon are going to behave in vacuum. So if we go all the way back to the initial discussions that we had about the interactions between charges, we know that these charges are going to interact with each other with repulsive forces that are generated by fields that are being produced by each charge. And we can put all that together into Coulomb's law. So Coulomb's law would tell us how the charges would interact with each other based on K. Or we could look at the individual fields that were produced by each charge based on K. But regardless of our trying to calculate field or force, we have yet to consider all the stuff that's in between these charges. And right now, you know, we're just assuming that it's empty space, it's vacuum. But what would happen if I were to actually put something other than vacuum between these charges? Maybe I put a large brick of glass or ceramic or polymer in between these two charges. Is that going to affect how these charges interact with each other and how they produce their electric fields? And the answer is yes, it will. And so this permittivity constant, this epsilon naught that we're using here, plays a part in defining that constant K that we've been using in every expression up until now. If you go back and look at every single derivation that we've done, K has been in that expression. Well, now all of a sudden our author starts to rewrite K as this 1 over 4 pi epsilon expression, because now we have to consider what's going to happen if I don't have vacuum in between my charges. Well, if that's the case, then we're going to have to go and look up a new permittivity value, because a different permittivity value is going to affect the K value that we've been using up until now. Now, don't worry, we're not going to start inserting different materials in between our charges just yet. We're going to wait until chapter 25 before we start doing that. This is the chapter on capacitors. So for right now, we're gonna stick with empty space, either vacuum or just air in between our charges. But we do need to start getting into the habit of writing K in this new method. Number one, because we need to be prepared for the day in which we do need to replace epsilon naught with a new value, and we should probably come up with some units for epsilon naught here. But we can actually get that from the K values that we had. Our force up here, force was in newtons, if you remember. And so K we had Coulomb squared for the two charges, we had meters squared for the R squared value, and so K had units of Newton meters squared Coulomb squared. But epsilon naught is made using a combination of our k value and just some constant values of 4 pi. And so the units for k are just going to be the inverse units for epsilon naught. For, in this case, we have Coulomb squared over Newton meters squared. So we need to start getting into the habit of writing k as 1 over 4 pi epsilon with all of our expressions. So here we have our point charge expression for electric field, now written in the updated version for k. If I want the electric force between two charges, well, that was k q1 q2 over r squared, so now we need k q1 q2 over r squared. Now, don't let this get you down, because even though we're writing this out in a more complex fashion, this is still k. This is still 8.99 10 to the 9. You don't have to make more work for yourself in your calculations. If you see this combination, that should make you happy, because you can say, oh yeah, that's k, that's 8.99 10 to the 9, and we go about our business, we go about our work. But now we can backtrack in all of these derivations that we've been working on. So for the disk here, oops, let's look at some of these combinations. We had right here, this was the expression for the infinite sheet of charge. We have 2 pi, we have k, and we have sigma. Well, let's rewrite this for the new and improved k value. We now have 2 pi over 4 pi, which is just going to be a 2. And so now we have an expression for the infinite sheet of charge, which is just sigma over 2 epsilon. This is actually very, very interesting, because there's absolutely nothing left in terms of the geometry of the system. There's no radius, there's no z value, there's nothing. Everything has broken down to just a combination of charge density sigma and permittivity with epsilon naught. It's actually kind of amazing. This is the only charge distributions combination that we're going to see that ultimately lacks any dependence on the geometry of the system. Now, since I've said that word geometry, I'll go ahead and make one more comment before we end this video today. Since we're going to be rewriting k as 1 over 4 pi epsilon, oops, the epsilon part, that makes sense for right now. Epsilon is measuring the behavior of the medium that exists between our charges. But where does the 4 pi come from? Well, that 4 pi is actually a result of the geometry in the system, and we're going to see where that comes from in the next chapter, chapter 23. Because with chapter 23, we're going to try to take a detour away from all of this intense calculus derivation, and we want to see if we can reproduce some of these field expressions using a more geometric approach. And so as we do that, as we set up the geometry, a common reoccurrence that we see in a lot of those setups is going to be that 4 pi, and that's going to come out of the geometry. All right, so we're going to have one more video for the chapter 22 material. We need to look at the electric field that is produced by at least one more charge combination, and then we'll go ahead and move on to the chapter 23 material and see if that geometric approach is any more user-friendly than what this calculus approach has been. So we'll see you at the next video.